Welcome to this video on the 10.2 notes. We're going to be looking at arithmetic sequences, and arithmetic should sound a lot to you like arithmetic. And so really we're talking about things where the terms have the same value either added or subtracted repeatedly. And so we're talking about an arithmetic sequence. You might see something like this, like here's just a sample. We could have something where we have whatever starting value. We determine my favorite number is 8. And then maybe I'm going to add 3 each time as my pattern. And so forth. This one, I would have this difference each time between each of them. We often call that the common difference. In this case, D each time would be 3. That's what I'm adding to each one of these. I could also have a situation where instead of the numbers increasing, they could be decreasing. So I could start with, for example, -5, and I could then go down by 2 each time in my arithmetic sequence. And remember, sequence is a list of numbers with a pattern here. So for these ones, the common difference each time is -2. And so when you have that common difference all the way through the pattern, that's an arithmetic sequence. And that could be either a positive common difference if the numbers are increasing by the same amount, or negative common difference if they're decreasing by the same amount. So a common difference, we'll use the letter D. And it is the amount that is added or subtracted. And when we think about subtraction, you could also think of adding a negative to each term to create the sequence. So anytime you have a situation where the pattern for one term to the next term is either adding or subtracting the same number each time, that would be called an arithmetic sequence. Sorry, you might hear my dogs in the background playing. I apologize. So for these ones, these are written in recursive form each time. And so on these ones, when we look at the first 6 terms, they've already given us the first term. The way I knew it was recursive was because of this notation here, which means the previous term. So if I want to find a sub 2, I would be looking at a sub 2 minus 1, or a sub 1, which in this case is 6 minus 2. This is the previous term. To find a sub 3, I would be looking at a sub 3 minus 1, or a sub 2, which is 4, minus 2, which is 2, and so forth. A sub 4 would be the previous term of 2, take 2 away with it, and I added a 0. And the pattern, if you look, is that the common difference each time is we're going down by 2, so the common difference is -2. And once you establish that, remember it takes at least 3 to establish a pattern, you could just keep doing that each time and not use the recursive formula. So the first 6 terms here would be 6, 4, 2, 0, -2, and -4. Well, if you look at the recursive expression, you can see that each time we are taking a prior term and we're moving 2 from it. So in this similar one, we're starting with the first term of 100. And what this pattern is saying is take the last answer, that's what this means, the previous answer, and add 30 to it each time. So the second term should be the previous answer plus 30. The third term would be the a sub 3 minus 1 would be a sub 2. So the previous term plus 30 more is 160, and so forth. Once we recognize this as arithmetic, we don't actually have to show the work, but we do want to make sure we're just continually adding 30 each time as that common difference. So for this one, we'd have 100, 130, 160, 190, 220, and then 250. You might not need to show all of the work. You want to be able to identify this as arithmetic when you see this type of format. Now, when it's recursive, you're going to see the common difference added or subtracted in to the previous term. When it's written in the general form, it's a little bit different. So just a side note really quickly. Let's say I took maybe example 1, and I recognized that if I do the term number as like an input, and then the output would be the value, If I took a moment to just plot these as ordered pairs, where I would have 1, 6, 2, 4, 3, 2, 4, 0. I'm not on a grid, sorry. 5, -2, and 6, -4. Perhaps if my handmade grid here were a little bit better. Do you see how this is linear? Anytime you have a common difference, it ends up looking like a linear function. Now, when we're talking about a sequence, it's not a connected continuous linear function. It's a linear pattern here, a linear correlation. But we're not connecting these because we're only using integers for term numbers. So there's like these gaps, these spaces in between. But each time we went down by 2. And so it was like this slope of down 2 and over 1 each time, down 2 and over 1. And if we think about how we write equations of lines, the way we write equations of lines is the format y equals mx plus b. M is our rate of change. That would be our common difference. B in this case would be the value of y when x is 0, which would be like a 0 term. So if I think about extending this pattern back the other direction, that would be at an 8. So interestingly enough, when we get to this general term for our explicit form, you'll see that we can write it in a similar format to y equals mx plus b. So in fact, that's the way I tend to write it. So now for the output, instead of y, we use a sub n. That's our general term. And then I like to write this as dn. D is our common difference. This is like our slope. N is our input variable. And then it would be plus a sub 0. Now a sub 0 would be the number prior to the list beginning. So it'd be if you extended the list backwards. It would be the one before a sub 1. This is the form that I like to use. I would say not everybody uses this form, so I do want to give you another form as well that is commonly used. They are the same. I like this one just because I like to think of these as being linear functions, and anything with a common difference would be. Alternatively, this is the one that's actually more common to be used. Feel free to use it if you prefer it. A sub n, that's my general term or my output, is equal to a sub 1, the first term, plus d times the quantity n minus 1. And this n minus 1 would always be there. And it's common if you write it in this format over here, the one that I have in black, is then you would want to distribute combine like terms, and it would end up looking like the one I have on the left. So it's really up to you. You can write it either way, and I will show you both ways, and please pick whichever you understand the best. All right, so on number 3, we want to find the 9th term. Sorry, little typo there. The 9th term of the arithmetic sequence. That keyword arithmetic lets us know that we could use this general term, where the first term is 6 and the common difference is -5. So a sub 1 is 6, and the common difference here is -5. So if I think about this expression, this would be like 6, and then keep going down by 5 each time. So it would look like that. So if I wanted to use the strategy that I tend to use, which is a sub n is equal to dn plus a sub 0, this is slope-intercept form. This is like y equals mx plus b. The y-intercept would be the term before we would start, and slope is the common difference. So you can use that if you want. You certainly don't have to. I'll show you both ways. So in this strategy where I use this one, a sub n is equal to the common difference, or my slope, of -5 times n. That's my input variable. A sub 0, this one's a sub 1. So a sub 0 would be before the list begins. So if I move to the left, instead of taking 5 away, I would add 5. That's how I do it. Alternatively, you could use this formula. A sub n is the first term, a sub 1, plus D times n minus 1. So a sub 1 would be the first term, which they said was 6, plus the common difference of negative 5. And then this n minus 1 is part of every single formula that you would use. I would then distribute and combine like terms, and I end up with negative 5n plus 11. So I get to the same answer either way. It just depends whether or not I'm comfortable moving backwards in that list to find the zero term, or the, like, essentially the y-intercept. All right, now this is the general term. That's not quite what they asked. They asked for the 9th term. So once I have the general term, if I wanted to find the 9th term, I would just substitute in a 9. So a sub 9 is negative 45 plus 11, which is negative 34. I am so sorry. My dogs are having the best time running around, causing a commotion in the background. I'm sorry if it's distracting. All right, for this one, we want to find the 8th term of the arithmetic sequence, where the first term is 4, and the common difference is 7. So what's happening here is each time we're going up by 7. And so our list looks something like this. So if I'm going to use the strategy I prefer, which is a sub n is equal to dn plus a sub 0. So a sub n is 7n. Remember, n is your input variable. And if I kind of work backwards and think what would have been, if this is a sub 1, a sub 2, etc., what would have been a sub 0? Well, if I move to the right, I'm adding 7. If I move to the left, I need to take 7 away. So this would be at negative 3. And then I want the 8th term. So once I have the general term, I could plug in an 8. And it looks like I get 53. Now, alternatively, you could just extend out the list. If I keep adding 7 each time, maybe I'll add right. We'll see how this goes. There we go. I could land at the 8th term. However, what if I asked for the 100th term or the 300th term? There's no way you would want to sit and extend out that pattern. So writing it in the general term first and then substituting it in for n, whichever term number you want, is commonly considered a pretty good practice. Oh my gosh, I'm sorry about my dogs. All right, number 5. Teachers in the U.S. earned an average of $44,600 in 2022. This is actually correct data. This is real data. The amount has increased by approximately $1,130 per year. Now, unfortunately, inflation has not increased at that rate. Inflation has increased at a much, much higher rate than that, particularly the last few years. We've seen inflation 4%, 5%, 6%, numbers like that. So what a bummer, although I think things are looking up a little bit educationally, at least in the state of Nevada, for teacher pay. All right, so we want to write a generalized formula for the nth term. Again, this is our general form, or for our general term, and we want to describe the teacher's salaries n years after 2000, and I think this says 2001, and it should say, I apologize, please fix that, 2002. Hopefully by the time you guys have this, I have fixed that on your paper. Okay, so a sub n, again, could be found by doing n or dn plus a sub 0. That's the way I do it. So a sub n is d. So the common difference is how much we're changing by. It's increased, so it's a positive common difference of 1,130 n. And then plus a sub 0 would have been the year prior to 2002, if this is a sub 1, right in here. Actually, I take that back. We're n years after 2002. So I think actually we are okay to use this. A sub 1 would be 1 year after. So that would be 2003. So if I want to use 2002, then this is already a sub 0 by the way that this has been defined. So a sub 0 is 44,600. So if I want to figure out how much teachers would earn by the year 2025, I would want to find a sub 25, which is, actually that's not true. Let's see, 2025 compared to 2022. would be 23 years later. So A sub 23 is what I'm going to be looking for. So 1,130 times 23 plus 44,600, which was my starting amount at time 0. So 1,130 times 23 years, and I'm adding on to that starting value, which was 44,600. So 70,590. 70,590. Right now, I can tell you that the average teacher salary in the United States is less than this, but however, we're not yet in the year 2025. So maybe if I calculate it for 2024, it'd be closer. It is a little bit less than this. The state of Nevada is a bit behind, so we're not very close to this quite yet. All right. Example 6, Americans are eating more meals behind the wheel. 2024, we averaged 32 a la carte meals per year, which is increasing by approximately 0.7 meals for each year. And that was in 2024. And so this one, we want to write a formula for the nth term that models the average number of cart meals n years after 2023. This one I did want to say 2023 so you could see the difference between this one and the last one. Notice that this is 2024. So A sub 1, which is the year, or 2004, was 32 because it was 1 year after 2023. Versus the prior one we did, they gave us A sub 0. So that is a little bit different between the two of these, which was done on purpose so that you could see the different ways on how to handle this. All right, so on this one, first we want to write the general term. So A sub n is equal to dn plus the 0 term. So A sub n would be equaling d. We're increasing. So this will be a positive common difference for d, 0.7. And then plus A sub 0. Now, if A sub 1 is 32, A sub 0 would have been 31.3. Because this would be 32, and then we're going up by 0.7 each time. And so A sub 0 would have been the one before that, so I would have had to take that away. Now, by the way, if you wanted to use the other formula, you certainly can. It's a great formula as well. Pick what you understand better. A sub 1 would be that 32, and then D would be the 0.7 times n minus 1. If we then distribute and combine like terms, we end up with the same answer. I'll just reorder this so that the variable term comes first. So whichever way you want to do it is fine. We end up with the same general term. We now want to find out how many car meals Americans average by the year 2023. Now, keep in mind, the way that the term number is defined is how many years we are after 2023. So we are now 20 years, or sorry, after 2003. So now we are 20 years later. I got that by just subtracting to see how many years have gone by. So we're looking for A sub 20. So once I have that general term, I can just substitute in a 20 and then add in, and then just plug that in essentially. And for whatever reason, I can't remember that value, 31.3. So if the pattern continues, we're now at 45.3 meals. Now, I know that looks like a weird number with the 0.3 meals, but averages often have decimal answers, even on things that aren't typically decimals, normally like meals. All right. Sorry, my dogs are having way too much fun because I'm ignoring them. They're causing a commotion. This one gives us a formula here. And by the way, you need to memorize this formula as well as whichever formula you decide you like better for the general term of an arithmetic sequence. You want to at least be able to recognize it. What we'll do on your test is we'll give you these formulas, but you won't know, is this one arithmetic? Is this one something else like geometric? So you do need to have some good familiarity with these in order for you to be well prepared for your assessments. But this is the sum of the first n terms of an arithmetic sequence. As a reminder, A sub 1 is the first term. A sub n is whatever term we're looking to find. So for example, on this one, we want to find the first 100 terms of this arithmetic sequence. Now, what if we tried to do this without the formula? Like one way to do this would be to try to list them all out. These are all these odd numbers. Imagine trying to list out all 100 of them. And see, kind of imagine where we would land and then add them all up. Now, there is actually going to be a strategy. Let's look at the formula first, and then I'll kind of explain to you why this formula works. I want to add up the first 100. So anytime we're adding them up, we'll use S for a sum. This is also the same as like saying that this is like a series. A series is where we add things up. This would be what we would call a partial sum, because we're only adding up a certain number of items. Like in this case, we're going to do the first 100 terms. Or a partial sum of this series. Remember, we can use that sigma notation as well. Would be another way for us to express what's happening here. All right, so if I want the sum of the first 100, so notice I'm using S instead of A. This is how I know I'm adding. I want to take N is 100. That's how many terms I'm adding up. Divide this by 2. And then I would do the first term, A sub 1, plus A sub 100, because that's what I want, is the 100th term. So A sub 1 I know. A sub 100 I don't know. I could kind of guess, like if I try to extend this out, but I really need to know for sure. So let's write the general term as a little bit of side work. The general term would be that common difference of 2 times n plus the 0 term, which would be the term before the list begins. If I want to add up the first 100 terms, I need to know what that 100th term is to do that. Remember, my common difference is 2 times 100 minus 1 would mean 199. So what is happening here? Why is this formula working? Let's do just a little bit of side work so that we can understand what's happening here. So if I'm adding up the first 100 odd digits, which is what's happening here, eventually as I get towards the end of this list, I would get numbers like 191, 193, 195, 197, all the way up to 199. Now, something that's interesting that's true is that if I add up the numbers on the end, and then I keep adding in the interior, I will keep getting this same sum all the way through. Really, really interesting. This is true for any arithmetic sequence. If I just keep adding up the ends and moving in. So I keep getting this sum of 200. Now, if you look at my formula, you're going to see that 200 is represented here by the first and the last terms, which is one way to find out what that portion of the sum is. How many times would I have that sum? Well, if I'm adding up 100 terms, I'm going to create 50 pairs. 50 pairs. That's why it's n over 2 in the front. This will tell you how many pairs you're making, and this will tell you what the sum of those two pairs would be, of the two numbers in that pair. So this ends up being 50 times 200, which, let's see if I can do any math, 10,000. You can, of course, use a calculator. All right, example 8 is very similar, so once you pause the video and give that a try. When you're ready, restart the video to compare solutions. All right, so here's the answer for number 8. So we're adding up the first 15 terms. So we're finding the partial sum here of this series. And so of the first 15 terms, that's why there's a 15. The formula is n over 2. This tells you how many pairs you have. And since we have an odd number of terms that we're adding up, it's like we have 7 complete pairs plus like a half of a pair by itself. And then the numbers start at 3 for the beginning of the list and at 45 for the 15th term. And I wrote my formula over here for the general term and then was able to calculate this out for a sum of 360. Well, this is really the same type of idea. The nice thing about this one is the general form here is already given. When we use sigma notation, this is the general form. We are using the variable I instead of using the variable n, but it's still the same thing. And so the first term here, if we plugged in a 1, would be 5 minus 9, which is negative 4. This 5 here is the common difference. If I plug in the second term, it should be 5 units larger. So if I plug in a 2, 10 minus 9 is 1, and so forth. And each time if I plug in a 3, I should be getting 5 units larger. So this is what this looks like. What I'm finding here is the sum of the first 25 terms. So I'm finding S of 25. So my formula is 25 over 2, and then I want to add up the first term, which is negative 4, plus the last term. So A sub 25, if I plug in a 25, would be 5 times 25 minus 9, or 125 minus 9, which is 116. Notice some of your answers can be negative. That can totally happen in a sequence. It does happen. And from here, I would just do that calculation. So I have 25 numbers, which would give me 12 and a half pairs. That's what that 25 times 2 is. And then times, in here looks like 112 for that sum of the first and last terms. So I end up with 1,400. All right, for this one, we want to find this sum. Again, we already have the general term given to us, which does save us a little bit of a step when we're trying to find, in this case, the 30th term to use the formula. So go ahead and give this a try. Go ahead and pause the video, and when you're ready, restart it. Okay, my solution for example 10 is up on the screen. So we're finding the partial sum of the first 30 terms. So I would have 30 divided by 2 is 15 pairs, and I want to multiply that by the sum of the first and the last terms. I can find that by using the general formula of 6i minus 11. All right, number 11. Your grandmother has assets of $500,000. One option that she is considering involves an adult residential community for a 6-year period beginning in 2009. So 2009 is going to be her first year. This model, A sub n, this is our general term, is equal to 1,800 n plus 64,130. It tells us how much it costs each year, n years after 2008. So 2009 is the first year. A sub 1 is the 2009 year. That's 1 year after 2008. So this is the first term. We could plug in and get that value by doing 1,800 times 1, and then adding on to that the 64,000. 64,130. So A sub 1 is 65,930. The common difference here, just as an FYI, is that amount that we're changing by each time in that slope position. Each year we're going up by $1,800. So the first thing is we want to see, does she have enough money to pay for the facility for 6 years? Well, if she's paying for it for 6 years, she's paying for it the first year and the second and the third all the way up. We're finding the partial sum of the first 6 years. And so I will use the formula of n over 2, or 6 over 2, times the sum of the first term, which would be that 65,930, plus the sum at the end. So at the end, 6 years later, after 2008, would be 2014. And so we would do 1,800 times 6, and then plus that 64,130. When we calculate this, this would be our total. And that ends up being 74,930. So the sum of all 6 years, if I do this calculation here, ends up being $422,580. So the answer is yes, there is enough money because she has $500,000. So she can pay for 6 years. All right, so now what we want to find is slightly different. We want how much it would cost for a 10-year period. So this is still a 10-year period of time, meaning we're still doing the first year, the second year, and so forth. So this time we're finding the partial sum of the first 10 years. So this would be 10 over 2. We're still starting as a sub 1 as in the year 2009 of 65,930. And then we're adding to that the last term, which would be the 10th term, which would be 1,800 times 10 plus 6,400 or 64,130. So that last term, a sub 10, is 82,130. Keep in mind, a sub 10 is the original, or is the amount of the 10th entry. S sub 10 is the partial sum of the first 10 entries altogether. So if I then complete this, we end up, it would cost $740,300 for the first 10 years. All right, and that is the end of the notes for 10.2.